All right, so what's the first one? Bond association, right. When a bond forms, the idea is that that substance takes atoms and forms a molecule. Molecule is a unit of a covalent substance, like a unit of a compound made of covalent, or a molecule made of units, right, that have covalent bonds. Those units are called molecules. A compound made of units made of ionic bonds is called a...
Crystals or ions?
No. It's called a...
Salt.
It's called a formula unit. One particle of a compound made of ionic bonds is called a formula unit. One particle of a compound made of covalent bonds is called a molecule. So when the molecule forms, it takes these atoms, it forms these bonds. We'll call them covalent bonds. And when those covalent bonds are formed, things become stable. The bond loses energy when it forms. That energy, if I want to break that bond, I have to put the energy back. So the bond comes apart. Yes? That bond energy is called bond association energies. Now, what's the question?
How is the strength of a covalent bond related to its bond dissociation energy?
How is the strength of a covalent bond related to its bond dissociation energy? And the answer is Mustafa. He's got it.
The higher the bond dissociation energy, the harder it is to break apart the bond.
The stronger the bond, the harder it is to break the bond. Excellent. Okay, what's next? All right, let's try to get through this. We have a good 25 minutes, so we're going to do quite well. All right, so I want to go through this. I want to go through this speedily. It might seem very fast, but it's on a video and you can rewind. Yeah, so it's good. Cool. Are we there? Okay, what's the next one?
How are resonance structures used?
No, resonance.
How are resonance structures used? What's a resonance structure? What's a resonance structure? What does it say? Anybody got that? Yes?
Wait.
Yes, what do you got? Do you have it? You do?
In my notes.
Okay, all right.
Oh, well.
A lot of people have it, but it's their question, isn't it?
Yeah, go.
Well, anyway, Annabelle, you go first.
It was just for the different.
Go ahead. For the Canadian team, Annabelle. Yes.
Yeah, a resonance structure is a structure that have two valid electron dot structure. So these two possibilities are just
I like
moving
this.
through together. They are always moving.
Excellent.
Yeah.
So what's an example of that? Do you have an example of that?
Ozone.
Oh, God, I like this. Ozone. Remember ozone? Looked like this, right?
Yeah.
Okay, so let's do the structure, okay? So it's going to be, that's ozone, O3, right? Remember we did this already? Yeah? So what is 666, right? 18 minus 4, correct?
Yeah.
14.
So what do you got?
14.
14. Complete the outer, that's 6 and 6, right? Yes? 12.
There's
2 left over,
yeah.
right? So remember, this has 12, this has 8, right? I want to put those in because it'll help you visualize this, okay? So what happens with this? What happens with this? Well, look at what happens. What electrons are going to come into here? These two are going to come down to here, or these two are going to come down to there?
Either.
No. If these come down to here, then the outer ones have 10, right? So these are going to come here. Can I erase these? Right? Yes? And you also have you can bring these two down, right? These are resonance structures.
Structures that have different ways.
Yeah, in other words, well, how did you put it, Annabelle?
There's two possibilities.
Two possible Lewis dot structure diagrams. And it's the shifting back and forth of those two diagrams. It's called resonance. It's called resonance. Okay. Do you have another one?
And it shifts all the time.
It continually shifts. Yes. Yes. How about this one? Is it this one
Yeah.
or not? Is that one?
I don't know.
Let's try that one out. We'll come back. Let's.
This is history. There's one missing.
No, that's not going to be one. Sorry, NO2. Sorry, NO2. Try that. Try that. So you have 5, 1, 6, 6 is what? 18, right?
Yeah.
Minus 4, 12. Sorry, minus 4 is 14, right?
Yeah.
Minus 12, 2,
So, yeah.
right?
Yeah.
So then you have these here. Right? Same thing, right?
Yeah.
So then you have either this, that structure you have,
The other way around.
or you have that structure. Cool?
Doesn't CO2 work the same way?
No, because it has two double bonds. There's only one answer to that. That's a good question, though. There's something called, and you can look this up for extra credit and tell me why it's true. Okay? You want some extra credit? You ready? When I think, as a chemistry person, I was a chemistry major, I was a chemist. As a chemistry person, when I think of resonance in chemistry, I think of the big kahuna. I think of benzene. Benzene. Look at benzene. When you're talking about resonance, if you ask a chemistry person, what's the first thing that comes to mind when you hear the word resonance? They're going to say, no, I don't want to know now. If we have time at the end, but I want to try to fly through this stuff. When you think of the word resonance, yeah, when you think of the word resonance, you think of benzene. Okay, what's next? So that's a good one. That was stolen by the Canadian team, the Canadian-South African team. Excellent. Well done. The unity of the northern and southern hemispheres. They called it the Canadian-South African team. Excellent. What's next? How are atomic and molecular orbitals related? Anybody got that? Yes. Atomic and molecular orbitals.
Molecular orbitals are usually constructed by combining atomic orbitals or hybrid orbitals from each other. What's this word?
Okay, you know what? Let's get back. You know what, guys? Why don't you study that a little bit more, and let's get back to that one. We'll come back. We'll circle around. Okay? But you sound like a textbook, though. I want you to kind of put it in a different language. We'll come back, though. Okay, we'll come back to that one. That's the difference. What does it say? How are atomic and molecular orbitals related? Okay, what do scientists use the Vesper theory for? What is the Vesper theory? What does that mean? What does that stand for?
The valence shell electron pair repulsion.
Wow, excellent. And that's someone who English is not their first language. That was excellent. Oh my God, I can't say that, and I speak English as my first language. Valence shell electron pair repulsion. And what does it use to do? Anybody got that? Yeah. What do we got?
Classifying molecules by their shapes.
Yes, classifying molecules by their shapes. You did the gumdrop lab, you remember?
Yeah.
All right, now remember the gumdrop lab. So how did you determine that ammonia, NH3, is trigonal pyramid and aluminum chloride is trigonal planar? How did you do that?
Its shape.
How did you those are two shapes. But how did you determine the shapes?
There's a table.
No, not using a table, just the ideas.
You use the theory.
Yeah, right. You use tables, correct.
Well, you notice that one looks like a pyramid, and you classify it as a pyramid, and you notice the other one looks like a hexagon. And you classify
Well, yeah, see, it's the electron pairs are going to repulse. In other words, these three hydrogen bonds would all be in the same plane, right?
Right.
It would kind of look like this. Right, wouldn't it?
Yeah.
120 degrees. But you can see how it's pushed out of the shell. See, they'd be like this. But they're pushed out of the plane. Not much, just a little bit, right? Do you remember that?
Yeah.
Pushed out of the plane by these. This electron pair, this unbonded electron pair. Whereas if I had something like aluminum chloride, which looks like this, no excess electrons on the central atom. Why? The metal.
Sorry?
It's a metal, right? If the central atom's a metal, it generally has less than 8, right? How many does beryllium hydride have? How many electrons? Beryllium hydride, do you remember?
No, neither.
BeH2. BeH2.
Beryllium's a halogen, right?
Doesn't matter. No, beryllium is not a halogen.
But it's in the
Barium's a halogen.
Yeah.
I mean, bromine's a halogen.
bromine, sorry.
That's on the.
Oh, that is
These
a
are
metal,
the
so
other
it
side.
doesn't have any.
Well, it's going to have a valence of 2, right?
Uh-huh.
That's going to have a valence of 2, so that's 4, right?
Right.
So that's beryllium, H,
So it fills each other up.
H. So it's going to be you complete the valence, it's completed, subtract off the bonds. 2 and 2 is 4. The total valence is 4. 0, so that's it. There's no extra pair of electrons on the central atom. The central atom, did that shut off?
No.
It's still working?
Yeah.
Yeah.
The central atom is what? The central atom is a metal, so it can have less than 8. So that's linear. These are repulsing each other relative to what? Relative to 180 degrees, right? All right, what's next? So the Vesper valence, what? What is it? Valence, shell, electron pair, repulsion. All right, what's next? In what ways is orbital hybridization useful in describing molecules? Anybody got an answer for that?
I do so.
Yes,
Orbital
Mustafa.
hybridization.
Mustafa, I'm telling you, you're really doing well today. Very impressive. Very impressive. Excellent. No, I'm not being facetious. You can never tell sometimes, right? Excellent. All right, what do we got?
Orbital hybridization provides info about the molecular bonds and the molecular shape, like the shape of molecules and the bonds between them. That's what it shows you.
All right, let me show you the big kahuna of hybridization. Are you ready? The hybridization that you really have to know. This is important, okay? Let's look at carbon. Carbon looks like this. This is 2s, and this is 2p. Do you agree that do you agree that 2 is the valence shell for carbon? Yes or no? Right? Okay. So, let me redraw this so it fits all on the same line. Okay, can you see it over here?
Yeah.
You see it over here?
Yeah.
Is that good? Can you see that? Okay, do you understand that if you do the electron configurations, it looks like that? How many bonding sites do I have? 2. I only have 2. But yet we know carbon has how many?
4.
It has 4, right? So what happens is this. You form this hybridization among the S and P suborbitals. And what happens? Yes?
Would you pass the S, one of the S electrons to the
Yes.
P?
Yes. She said you pass one of the S electrons to the P. Yes, but that's a little bit... That's true, but what happens?
An s electron goes to the p orbital, and that way there's it's more stable.
It's more stable, that's true. An S goes to the P, it's more stable, but
But we still have 3, so the one S is combined.
No, that's 4 bonding
No, that's
sites.
4, yeah.
There's 1 in an S orbital and 3.
we have an argument here. I like this. I like this. It's Egypt versus Canada. I like this. The World Cup of Chemistry. Excellent. Are you speaking French? Excellent. Oh, I like that. I like that. Again, last time I spoke French, they took me to the hospital. My windpipe collapsed. I couldn't pronounce the words. Terrible. I'm kidding. And I was going, really? Wow. All right. Okay, all right. I was only kidding. Okay. Now, so, yeah, but what happens is this. You form four suborbitals that are the same. So it's kind of like a new system. Here I have a 2s and 2p, right? They're separate. They're at different energy levels, right? This is a new sublevel. It's a brand new one. It's not an S and it's not a P. It's called an sp3. It hybridizes. What happens when you combine a donkey and a horse? You get a hybrid, a mule. You get a hybrid, right? Yeah, you get a hybrid. Well, what happens when you combine 2s2 and 2p2? You get a hybridization sp3. It's brand new. You have spdf, yes? Now we also have sp3, brand new. And the thing about it is they're all at the same energy level. And it's more stable than the sum of these individually is higher in terms of energy than the sum of these 4 together. Oh, that was well said, wasn't it? Sarah, you look impressed. The sum of these individually, the sum of the energy of these individually is greater than the sum of these together. Correct? So now I have an electron like this, I have an electron like this, I have an electron like this, and I have an electron like this. Now I have 4 separate bonding sites. Here's carbon, bonding sites 1 through 4, right there. And they're all at the same energy level. So now I can form 4 separate bonds. Do you get it? Yes? Abby looks like that. Abby looks like, I'm from Missouri. Okay?
You showed me.
You showed me. Uh-oh. Is it gone?
Something.
What happens? What does it
Still
say?
going, it's just like...
Yeah.
What's going on? I just got a, like
a
a
reminder, I guess.
reminder. Here, well, let me say it. Let me say it. What is that? What does it say?
Secondary meeting.
Secondary. No, don't. Yeah. Oh, is it not taping? Maybe.
It still tastes
It still tapes.
Yeah.
Okay, I got like a reminder on it, like a meeting. Like I really care about a reminder. Do I have a meeting
Why would it
today?
be there?
Oh, well, you're going to the doctor.
Oh, we have a meeting today, don't we? Oh,
Oh, whatever.
as I used to say, brivets and broomsticks. Okay. It's a silly thing. Instead of saying bad words, we used to say brivets. Brivets and broomsticks. It's silly. Anyway, couldn't say bad words as kids, so we had to say brivets. Brivets and broomsticks. Yeah. You know. Okay. Now, what's next? We're on a roll here, guys. Huh? We got 10 minutes left. Can we do this? Shall we skip some of the easy ones? All right. In what ways does blah, blah, how do electronegativity values determine the charge distribution of the polar bond? Right? It's in the direction of the dipole moment, right? So the greater the electronegativity, the greater the dipole moment, and the shift in the charge will be in the direction of the dipole moment, correct? Yes? The classic example that I use is this. If I have hydrogen chloride, right? The shift is like that. towards the chlorine, correct? So there's an unequal distribution of charge in that covalent bond. You put that in water, you completely dissociate and becomes ionic. In the gaseous phase, that remains covalent, polar covalent, correct? All right? What's next? It says, how do strengths of intermolecular attractions compare with the strengths of ionic and covalent bonds? Anybody have the answer to that? Yes.
The strength of intermolecular attractions is is the strength between it's how strong an ionic bond is, or how strong a covalent bond is, right? No, it's not.
No, that's not correct. The strength of intermolecular attractions.
So between molecules?
Between molecules, right.
The stronger an ionic bond, the stronger its molecular bond will be. Molecular bond.
No, why don't we work on that? Well, we'll come back to that. Is that okay? Do we have an answer?
I think they are.
Annabelle, go ahead.
I think they are weak.
Yeah.
What's weaker? What's weaker?
In a molecule.
The intermolecular
Yeah.
forces are actually very weak.
Yeah.
What happens is, what makes them actually strong?
Hydrogen bonds.
Well, the number of them. They're just,
Yeah.
you just have the number of intermolecular attractions. When you increase the number of them, the total effect will be greater, correct?
Strength with number.
Okay. What's next? Why are the properties of covalent compounds so diverse? Anybody? Do we have that answer?
Yes.
Yes.
Properties of covalent compound are diverse because of varying intermolecular attraction.
Yes. You see, when you talk about ionic bonds, you talk about crystalline structures, correct? When you form salt crystals, etc. But when you're talking about covalent bonds, you're not talking about crystals, gases, liquids, etc. And you bring into it an extra factor, and that is called intermolecular forces. It's the intermolecular forces which make the properties of covalent substances so diverse.
Oh, so that's the answer to the other question.
Correct. Well, no,
Well, it's part.
the answer to the other one is he's
Covalent
talking.
bonds are in a strong way. The molecular bonds between.
They're weaker. The intermolecular forces between
Covalent bonds are weaker than.
covalent molecules. You see, covalent bonds hold atoms together, carbon and oxygen.
Molecular
Okay.
bonds hold
No. Listen. So, carbon and oxygen in CO2, correct? You have covalent bonds between the carbon and the oxygen, correct? But then intermolecular forces are those forces between two carbon dioxide molecules. So you have bonds between the carbon and the oxygen, double bonds. But then you have the attraction, they're not bonds, they're attractions, such as hydrogen bonds are attractions, they're physical bonds between two water molecules, or a hydrogen bond is the physical attraction between hydrogen and
hydrogen.
between hydrogen and
Hydrogen with
an electronegative element, correct? Or that element in a compound. Like, for instance, it's on itself. That's water, correct? That's hydrogen, delta, lowercase delta, plus, negative, plus. So it lines up like this, right? This attraction between these two, this partially negative and partially positive, the attraction, it's not chemical, it's physical. It's physical. And that attraction is called a hydrogen bond because it's between hydrogen and an electronegative element. So it goes like this. So you can literally form this network
Of molecular.
Yeah, you have this networking of physical attractions called intermolecular
That's
bonds.
sort of like a drop of water, right?
Well, the water is held together by hydrogen bonding, essentially. It gives water a lot of its properties. And when we do a chapter on water, hydrogen bonding is going to become very important. Okay, let's look at this. What's next? It says, what is the octet rule for both atoms and ions? We don't want to go near the octet rule. We know what the octet rule is, okay? All right, what is an ionic compound? Too easy. How do you write the formula of an ionic compound? It's too easy. What are polyatomic ions? Too easy. Why? How do you name and write formulas for covalent bonds? We did this Greek prefix system.
Yeah.
Greek prefix system. Yes. Sulfur dioxide, dinitrogen monoxide, dinitrogen pentoxide, carbon dioxide, carbon monoxide. We use the Greek system, correct, for covalent compounds. May I call it covalent compounds, or we'll call it molecules? Okay. What else? How do you identify binary and ternary acids? You want to review that. Binary acid is what? Hydrogen and a nonmetal, right?
Yes.
Hydrogen, HCl, HI, right? H2S, hydrochloric acid, hydrosulfuric acid, hydroiodic acid. Prefix is hydro, suffix is ic, right? Hydrochloric, hydroiodic, hydrosulfuric. Ternary acid is the polyatomic ion. If it's 8, it becomes ic. If it's ite, it becomes us, right? Sulfite, sulfurous. Sulfate, sulfuric.
No hydro.
Phosphite, phosphorus. Phosphate, phosphoric. Did I say that right? Phosphite, phosphorus. Phosphate, phosphoric. All right, what else? How are the number of valence electrons determined for a specific element? Too easy. Let's go down. Cations are, has nothing to do with cats and dogs. Cations are positively charged ions. Anions are negatively charged. What's a cathode?
The cathode is a
Negatively charged electrode that attracts cations. Cations to cathode. Yes?
So are these all the questions that are going to be on our test?
It's from there, but if you give me like another 2 minutes, then I'll be done. Okay? Everything else is read up on metals. Okay? Read up on metals, alloys. All right? Shall I give you 2 questions from the test?
Yes.
I gave 3 to the last class, but they're on the web. They'll be on the web, so 3 and 2 is 5. So now it's 5 separate ones. I'm being far too nice. Don't tell anybody. Okay. Pick a number between 1 and 40.
35.
1 in 40.
40.
Pick a number between 1 and 40.
35.
35. Okay, here we go. It's 35. How do atoms achieve noble gas configurations in single covalent bonds?
How do what?
I'm not repeating it.
That's
How do atoms achieve noble gas electron configurations in single covalent bonds? That's a good one. It's a good one. That's all I'm giving you. Pick another between 1 and 40.
29.
No, you're not picking another one. You know?
27.
Oh, wait a second. Abby?
27.
27, I like that. Everything's very high today. Maybe I should, I like that. All right. Which of the following covalent bonds is the most polar? How would you determine that?
As the largest difference between two electronegativities.
Yeah. Am I giving you electronegativities on the test?
Maybe.
Well, obviously, because
No, I'm not.
it's a question about.
Maybe I will. All right, fine.
So the questions you're doing during class, if we answer those, they'll help us prepare for the test.
Absolutely. The test was, look, These questions were generated from the text. These are from the text.
Oh, I said test.
No, listen to me carefully. These questions that we worked on today are in the text. Okay? Yes? Okay. The test is on chapter 7 and 8. Right? The test is taken straight from the textbook. So what do you think? Excellent. She's got it, I'm telling you. How we doing? We doing well? Abby, what do you think? Excellent. Anybody else? Yes?
If you want to look at the other models,
We have a question.
hybridization.
I wouldn't worry too much about that hybridization. I'm going to put a little bit of this is molecular bonding. It's difficult, so I'll put a molecular bonding curve on the test a little bit because it's hard and we're trying to get things in before the midterm exam. So there's going to be a little bit of we'll call it simply a compassion curve. Is that good? You like that? You like the name of that? Excellent. Hey, listen. Hey! What I used to say last year at the end of class, do you remember, guys? Or is anybody watching from last year? I used to say, be careful out there. Got it? Have a good day.
Good.